Okay, let's dive in. Imagine, if you can, the entire universe we see. All those galaxies squeezed down. I mean, smaller than an atom.
That's the picture. Yeah, a point so early, space and time were just emerging, just this incredibly dense, hot soup of energy.
That's the scene our source material, the story of cosmic inflation, sets for us.
Exactly. And that's our guide for this deep dive into the universe's, well, absolute infancy.
So our mission today, using this source, is to really get our heads around cosmic inflation. What is it? Why did we even need it? And, is there actual proof?
Right. The source focuses on this event unbelievably fast, right after the universe's birth. We're talking like 10 to the minus 36 up to 10 to the minus 32 seconds, just a sliver of time.
That's hard to even imagine. And the basic Big Bang, that describes expansion, right? That's fundamental.
Oh, it is. But our source points out there were some big puzzles left over, things the standard picture didn't really explain well.
Okay, like what were those main problems?
Well, the book really focuses on two. First, the horizon problem. Why is the universe so incredibly similar everywhere we look? Temperature, structure, across huge distances.
Regions that shouldn't have been able to talk to each other yet.
Exactly. They're too far apart for light to have crossed the distance in the age of the universe then. Yet they match.
Okay, what's the second one?
The flatness problem. Observations show the universe's geometry is, well, incredibly close to flat. Not curved like a sphere or a saddle, just flat. The standard Big Bang didn't predict that. It seemed like a massive coincidence. Needed fine-tuning.
Okay. So this is why inflation theory popped up in the early 80s, as the source explains. How does it tackle those issues?
So the core idea, according to the book, is that in that first tiny moment, a strange kind of energy field, they call it the inflaton field, took over.
An energy field?
Yeah, a scalar field. And it drove this wild expansion, exponential, superluminal expansion of space itself.
Whoa, hang on. Faster than light. Doesn't that break the rules? Einstein's speed limit.
That's a key point the source clarifies. It's not stuff moving through space faster than light. That's the limit. This is space itself stretching. The fabric of space-time expanding incredibly rapidly.
Okay, space itself stretching.
Got it. The scale is immense. In that tiny fraction of a second, it blew up the universe's size by a factor of at least 10 to the power of 26. Maybe much more.
That's just nuts. Taking something proton size and making it bigger than everything we can see now.
Pretty much, yeah. In almost no time at all.
So besides fixing the flatness and the sameness problems, what's the other big thing this massive stretch did, according to the book?
This is maybe the most amazing part. It explains where structure comes from, where everything came from.
How?
The source talks about quantum fluctuations, tiny, unavoidable jitters in that primordial energy field, little quantum fuzziness.
Right, even in empty space, there's that quantum foam sort of thing.
Exactly. Inflation took those microscopic irregularities and just stretched them out to enormous cosmic scales.
So tiny quantum ripples got blown up into the blueprints for galaxies.
That's the idea. Those slightly denser or less dense spots, magnified by inflation, became the gravitational seeds, the places where matter started to clump together later on.
So they formed the scaffolding for everything. Galaxies, clusters, the whole cosmic web.
Inflation naturally generates these starting irregularities that we absolutely need to explain the universe we observe.
Okay, but how do we know this isn't just a neat story, theoretical hand-waving? What's the evidence the story of cosmic inflation presents?
The main evidence, the really compelling stuff discussed in the book, comes from the cosmic microwave background, the CMB.
Ah, right. The afterglow. The universe's baby picture.
That's the one, from about 380,000 years after the Big Bang. And we've mapped it incredibly well with satellites like CubeSat, WMAP, and Planck.
And they found tiny temperature differences, right? Hot and cold spots.
Exactly, tiny variations. And the pattern of those spots, their statistical properties, how big they are, how they're distributed, it's described in the source as the fingerprints left by inflation.
Fingerprints.
Yeah. The specific type of nearly scaling variant, nearly Gaussian fluctuations. It's precisely what the simplest models of inflation predict you'd get from stretching those quantum jitters. The match is really, really good.
So the details in that ancient light map strongly suggest inflation happened.
It's considered powerful evidence. The detailed structure seen in the CMB fits the predictions of inflation remarkably well. It's the leading theory for that very early time, largely because of this evidence.
Okay, let's try to sum this up then. Based on the story of cosmic inflation, the idea is a tiny fraction of a second after the beginning, there was this short, absolutely explosive expansion of space itself.
Driven by a sort of energy field, yeah.
And this fixes the problems the old Big Bang picture had with uniformity and flatness.
Right. And crucially, it takes tiny quantum fluctuations
Those little subatomic jitters.
and blows them up to become the seeds for all the galaxies and cosmic structures we see today.
And the best evidence is hiding in plain sight, in the patterns of the cosmic microwave background radiation, those fingerprints in the universe's baby photo.
That's a good summary. It really changes the picture from a smooth, gentle beginning to something incredibly violent and fast.
Yeah, it's a different feel entirely. And thinking about that, why does knowing about this incredibly brief, explosive start matter for, understanding the universe you live in now?
Well, it tells you that the largest things you see started from the smallest things imaginable. The link is profound.
Which leads to a final thought, maybe something for you listening to chew on. If these quantum-sized irregularities, totally invisible to us, could be stretched by inflation to seed the entire large-scale structure of the cosmos, what other tiny fundamental processes, maybe ones we haven't even discovered yet, could be shaping reality on scales we can barely comprehend?